The educational background of Professor Lippmann is that he received his bachelor's degree summa cum laude in physics from Brandeis University in 1972, and followed that with his PhD from MIT in 1977. That was on atomic physics. He's had many honors. I'll only mention two of them. He was Phi Beta Kappa, and in 2005 he received the Excellence Award from the Optical Society of America and the Engineering Excellence Award. He's well known for something that's completely different than what he's going to talk to us about tonight, and that is that he is helping to build a telescope that would allow for the optical detection of Earth-like planets around nearby stars. And yeah, I don't think that's part of tonight's discussion, but people might want to talk to him privately later on about that. He just told me that the Japanese are helping to fund that project. But tonight's lecture is going to be titled "Teaching Engineering with Antiques," as you can see up there on the overhead. And please join me in welcoming Michael Lippmann.
Thank you, Mark. So bachelor's in 1972, I wonder if that makes me an antique. So it's teaching engineering with antiques by antiques. So it's my good pleasure to be here this evening. And this lecture is closely connected to a course that I've been teaching for about 10 years on engineering in the modern world. It's about the history of engineering from the Industrial Revolution to the present. The topic today is slightly different. It's dealing with antiques and collectibles, and it's connected, though, that many of the objects that are represented tonight are also ones that we talk about in the course. And I'm also starting a little earlier in the time period. We're going to go all the way back to the 17th century today, as you'll see. So there's one theme that I want you to think about as we're going through the lecture, and that's the concept of reversibility. Now, what I mean by reversibility is that many of the objects we're going to look at can be looked at forwards or backwards. So, for example, if you looked at an electric motor and you apply voltage to it, the motor spins. But you can also use an electric motor as a generator. That is to say, you can spin the armature and then use it to generate electricity. So it works both ways. And we'll see that that's a theme that will come out today, both literally and figuratively. So Mark, if I could have the first slide. So this is an important slide, and it's the one I start with, and it's the one that I'll end with as well. And it has to do with consumer goods. And it's consumer goods from the time period from 1900 to 1980. So, and it's the vertical axis goes from 0% to 100%. 100% is total saturation in people's houses. This is based on census data. And what's shown here is the telephone, the automobile, radio, television, and the electric light. Next slide. So the first thing to think about, I want to categorize this. I want us to look at engineering works. We'll start off with transportation, of course. The automobile, we note that the automobile is essentially absent prior to 1900, and then it comes on over a period of time. And this is a Model T Ford. And we think about transformations. You think about the transformation from animal to machine. Next slide. Then the next technology that we look at here is in the information area. And it's a transformation from code, that is Morse code, which is what you had with the telegraph from the 19th century, to voice, which is what you have with it in the 20th century. And so here we have a 1910 telephone. And we see again, starting at the beginning of the century. Next slide. And then power, that's another category. And again, the transformation for power, this is an electric light. This is Edison's early electric light. It's 1879. The transformation was from kerosene to electricity because electric lighting in the 19th century was basically kerosene or coal gas. And in the 20th century, it switches to electricity. So these are all transformations. Next slide. So those three areas, power, information, and transportation, are going to be very important for us. And then we can look at this in another way. We can look at it from the perspective of economics. So what does that mean economically? Well, again, if you think of the companies that grew out of these different industries, the power industry, General Electric, started with Edison General Electric and then became General Electric. So that starts with electric light. In the information area, it was the Bell Telephone Company, beginning of the Bell Telephone Company at the end of the 19th century, on into the 20th century, and with AT&T. And of course, in the transportation industry, in 1903, the Ford Motor Company gets started, right at the beginning of the century. So that's economics. Next one. We can also think about it with a template from the perspective of politics. So if you think of power, the TVA, that's the Tennessee Valley Authority under the New Deal, under FDR, and its purpose was electrification to the area of Tennessee Valley. So that's power. Information, we can think of what happens with the radio, and then later the formation of the Federal Communications Commission in about 1927 was the Federal Radio Act. And also, again, a political result of Congress acting and creating federal regulation of the airwaves. And then in the transportation area, we can think of the first bi-state agency, the Port Authority of New York, whose function was for transportation infrastructure. First starting with railroads, that was in 1921, and then moving to automobiles, and then moving to airplanes. So again, this is where politics plays into those three categories. Next slide. And then you can also ask the template, you can ask about what it does to people. So in the power, we have lighting, personal lighting. It makes the workday long, and it makes the night safe by public lighting. Great change in society as a result of that. In the information area, you're able to not only send messages by telegraph from station to station, but now you can start having personal conversations across from city to city, and then by 1915 across the nation. And then in the transportation area, well, at the end of the 19th century, people were getting around on bicycles, and then bicycles were very popular in the 1890s, and then the automobile comes in, and then of course everyone had an automobile very quickly and went to tour the countryside. Next slide. So now the categories that you can use to describe these the power, information, and transportation. We break them down, I do this in our course and I'll do it today, into 4 areas. And if anyone asks you to define engineering, it's tough to make a definition of something as broad as engineering. But it's relatively easy to break it into categories. And the categories that we use are structures, machines, networks, and processes. So structures is civil engineering, machines is mechanical engineering, networks is electrical engineering, and processes is chemical engineering. This kind of categorization is actually, it's done in other areas. Samuel Morse, when he formed the National Academy of Design, he was a professor of art before he developed the telegraph. He was interested in defining the art world, and he defined it in 4 categories. And those were painting, engraving, sculpture, and architecture. So again, it's very hard to define art, but you can define it through categories. We define engineering through these 4 categories. Next slide. And if you think about structures, And what structures, again, power, information, transportation? Well, clearly hydroelectric dams. It's a very large structure. The image down at the bottom here is by Charles Shaler. It's a painting. It's a painting of Hoover Dam, showing the tall Hoover Dam, the lattice towers, and the insulators for bringing the electricity. That's the power dam. So this is what the artist does for us in helping to interpret that. In the information area, we can think of the tall towers that are used for wires, transportation, we can think of bridges. These are all large-scale works as a result of civil engineering. Next slide. In the machines area, again, power, information, and transportation. We can think of turbines. Here's a Pelton turbine. Again, this is from Charles Shaler's photo essay. It wasn't a photo essay, it was an essay, an artistic essay in Fortune magazine in 1940. It was an essay about power. You can also think in the, for machines in the information area, think of relays that are needed for telephone networks. In the transportation area, we can think of the machines, the automobiles themselves. Next slide. For networks, again, power, we can think of the power grid, this very large grid of wires, very important for the development in the early days of electrical engineering. Then there's the information lines, the telephone lines, which today, if you were to talk about the lines, you would be talking about lines that would be fiber optic lines for sending information. And then the transportation, this would be civil engineering, so we see that the networks is not just electrical engineering, but civil engineering participates in roads. So you think of a network of roads. And then the last one for processes, here we see an image of the ladling of steel, and we think of power, think of engines, automobile engines made out of steel. The information, it's really copper, and then later glass today. And then processes, oil, the processing of oil is how chemical engineering got started in breaking crude oil into gasoline and other products. Next slide. So this is now another important slide for our course, and it's before we get into the antiques, I thought it would be useful for background. And it's three perspectives that you can use for looking at engineering works. And the three are scientific, social, and symbolic. We think of that like alliteration. My memory's not so good, so it helps me remember what they are. But we think of this, it couples very nicely to what we do in the university. So you think of the sciences, the natural sciences, the social side, you can think of social sciences, and then the symbolic side, you can think of the humanities. And we try to look at engineering works from all these different perspectives. And it does certain things for us. So you know at the top here it says language. So science gives us a language for which we can describe engineering works. And we use formulas, and I should tell people to lock the doors here because there will be formulas in what I will follow up with. So don't be too frightened. But formulas are very important for us to express relationships, but they can also express relationships that are important in terms of economics or symbolism, visual aspects of the engineering works. The social side, by social we mean political, economic, cultural, and historical. Those all come together, and they help us understand how it is that engineering works come about. So it's not just that it happened as a result of some great individual, but rather there's a context, and that context is political, social, economic, and historical. And then so that's purpose. And then the artists come in. I like the use of art especially because it helps us go and look at the engineering works and ask the question, what's it important? Why is it important? Or why is it dangerous? Or whatever. The artists tend to sort of re-normalize us and sort of get us to look at the engineering works in a different way. Okay, next slide. So now we're going to get to the works that I'm going to describe. There are many of them we work with in our course and that I've had experience with, and I have a subset of them here to represent the four centuries. Okay, so we're going to start with clocks. Here we see a tall case clock. It's a grandfather clock. Next slide, please. This one's a little odd. It's the first time I'm putting it in here. It's a car jack. It's the jack from a Model T Ford. You'll understand why it's there in a little bit. It may seem a little frivolous, but I think you'll understand in a minute. Next slide. Then we're also going to look, many of these things are ordinary objects. This is a pitcher pump. It's the kind of pump that you'd see on a farm for pumping water out of a well. Next slide. We have a steam engine. So this is a model steam engine that we'll see in a bit. We have the automobile. This is a Model T Ford. Sometimes when if this lecture was earlier in the day, I would have brought the Model T with me. If you look very closely, you'll see this is Tawfiq Kaladi. He's one of our seniors driving, and I'm sitting next to him, and we're over at the Forrestal campus, and he's getting a driving lesson in the Model T Ford. Next slide. And then phonograph. So we'll look at Edison's phonograph, and this is a wax cylinder phonograph. Next slide. Now, what we also will look at are the engineering ideas that underlie all of those objects. And there, I have 6 of them that are there: the pendulum, the pulley, the gear, the piston, the diaphragm, and the spring. So let's start. So we'll start with pendulum, pulley, and gear. Next slide. So here we see Rebecca Gillespie with a clock. It's a tall case clock that sits in our faculty club, and we managed to get permission. It was a gift of the Adams family. The Adams family is the one that gave the Tigers behind Wigan Clio Hall, and they also gave some other objects. But it seems that in shipping the clock from their estate to campus, some parts were lost. And for at least 35 or 40 years, this clock just sat as something to look at. And I admired it going back and forth to lunch and faculty club. And when Rebecca came to me and wanted a project involving mechanics, and since I have been interested in history, I said, well, how about let's try to restore this grandfather clock? She thought it was a wonderful idea. It took us about a month to get permission from the university to do this. This was not easy, I will say, but we were able to do that, and we opened it up, and lo and behold, next slide, something's not right. There's a pendulum. Okay, no pendulum. Next slide. So we took the clock apart and put it on a test stand, and here is the guts of the clock. It's a brass movement. And then there are suppliers out there that will supply missing parts. So we went to Merritt's clock parts. I think they're somewhere in Pennsylvania. And we bought, next slide, and we bought a pendulum, and we bought weights, which was missing. So the diagram here is very important. And here's also our first formula. So one thing to note, I want you to look at this diagram. We're going to look at the clock in a moment. The first thing is that we have a pendulum, and the pendulum, there's a pivot up at the top, and it's attached to this anchor, and that anchor engages with this escape wheel. It's a 30-tooth escape wheel, and the second hand is physically attached to the escape wheel. So as the escape wheel turns, the second hand advances. And we see that there's a weight over here, and it's wrapped around an arbor. Next slide. So in thinking of the parts that I started with, the parts are the pendulum, the gear, and then the pulley. The pulley we see is there's this cable that's wrapped around, and then the weight is supported around, around that pulley. Next slide. So now if we think about the way an engineer would look at these objects, and you can, first thing you would ask is say, where's the motor? Well, this is a weight-driven motor. So just imagine we have that pulley. There's a bearing that it rests on, a cable's wrapped around it, a weight's hanging down, and if I let it go, of course the weight drops and then the pulley rotates. So that is a transformation from a falling weight to a rotation. So that is a weight-driven motor. And then you can look at the weight itself and you can say, well, that's the fuel. When the weight is up high, the tank is full. Right? When the weight's all the way down at the bottom, the tank is empty. And then the other piece that's important here is the pendulum with the other parts that are connected to it, the anchor and the escape wheel. And it serves as the governor. It determines the rate at which the weight falls and the rate at which the pendulum rotates. And there's a formula that we have down at the bottom here. T is in the time that it takes for one period of the pendulum. And L is the length of the pendulum. So that's a formula that's a relationship between time and length. Okay? And it's a formula that we'll work with in a minute. Next slide. It says demo of the Connects clock. Okay, so now let me see if I can bring up the Connects clock on our screen here. Okay. So let me zoom back here so we can see the clock, and then we'll zoom into it. I can get almost the whole clock in here. And so I'm going to raise a weight on this clock. So this is a model of the clock. I have a little pulley in the back here, a very tiny thread. The weight is made of Connects. This is a building toy that I'm rather fond of. And let's see if we can see what's happening. So you can see the pendulum is swinging. And if I look very close up at the top here, I can see what's happening. As the pendulum swings, I get a catch and release of the escape wheel. It's called a recoil escape. And it's purely mechanical. It's a weight-driven clock. Something to note is, let's take a look at the weight. Notice every time it ticks, you get the weight shaking. What you see is that every time it ticks, the weight is dropping. Okay, so it's using up energy, it's using up its fuel, and it's keeping the pendulum swinging through that recoil action. All right, so that's the Connects clock. And we'll just let it continue to run. Okay, can we go to the next slide, please? So now we come to our formulas. So the relationship is between time and length. How tall should the clock be? That's a question that we can ask. Now, the escape wheel has 30 teeth in it. So a tick releases half a tooth, and then a top releases the rest of the tooth. Okay, so it takes 60 seconds to go one full revolution. Next slide. So the answer is that the pendulum has to be about 3 feet in length. And so the reasoning for that is the escape wheel has 30 teeth. So a tick-tock cycle must be 2 seconds. And then I'm going to use the units that were used at the time. We're going to assume that the gravitational constant G is 32 feet per second squared, or 9.8 meters per second squared, if you like. So 32 feet per second squared, and 2 pi over here has a value of about 6. So we want T to be 2, and this is 6. That means the square root of L over G has to be 1/3. Okay, so 1/3. Okay, which means L over G has to be roughly 1/9. Okay, so that means if G is 32, suppose it was 27, then 1/9 of 27 is 3. Okay, so therefore L is 3. So tall case clocks, the reason they are tall is that they have an escape wheel of 30 teeth, 60 seconds to go around, and that is all from this formula. Next slide. And then you ask the question, who are the key people? So we like to use stamps on this. Stamps are sort of public art, right? So they've been validated by some government. And here we see Galileo. It was Galileo that had the idea of using a pendulum to time objects. He used it for timing experiments. And Christian Huygens, somebody who is well known in the optics field, also got this idea from Galileo and turned it into a clock. And he did that in 1656. And here is a stamp, and this stamp reminds us that he was from Holland in the Netherlands. Next slide. And here we can see Rebecca working with we were working with a clockmaker. I forgot to tell you, one of the conditions that the university had that we let us go and touch this clock is we had to work with their clock restorer. It's the Pennington Clock Shop, Dean Morrison in Pennington, very nice man. So he allowed us to use his tools, so we did the restoration, the initial restoration in his shop. So here's Dean. We have the clock in parts. Next slide, please. And here we see Rebecca. One of the things Rebecca did is the brass had worn out in places, the pivots had worn out, so we put new bushings in the clock and repaired a few of the parts. Next slide, please. And then we assembled it. And here you see, this is if you look very closely, you'll see a second hand going there. Okay, the second hand is attached to the escape wheel, and it's operating. And here here you see the pendulum swinging back and forth. So we were able to get it going, and she was able to graduate. She, by the way, is now at the Museum of Natural History in New York City, working in museums. It was a perfect place for her to wind up as an interest in mechanical engineering and also interested in history. Next slide. Now, again, the artists help us look at this. So this is Winslow Homer. It's 1868. It was a story about life in the textile mills. And this was called Bell Time at the Textile Mill. Bell Time. Here's the bell tower. Okay, these were bells driven by clocks. And it helps us remember that clocks were a source of information for people at the time. And it ordered the day. The entire day of the textile workers was organized around bells. Next slide. Now here's another way to look at the clock, and it's a different way. We look at it as a timepiece, but we can also see that the swinging of the pendulum gives rise to that falling weight. I showed you how that worked before, right? So remember I said that one of the concepts that I had wanted to introduce today was the idea of reversibility. So I could ask you the question, what is the reverse of a clock? So I was thinking about that, and I said, well, it's obvious. Next slide. It's a car jack. And we'll take a look at this in a minute. So we have a swing to a falling weight, right? And then in a car jack, you swing the crank up and down, and then you get a rising weight. You raise the car. And if you look very closely, you'll see that there is a gear, and then there's it's a ratchet and a pawl. And the ratchet and pawl is just like the idea of the anchor and the escape wheel, but it's running in the opposite direction. So I would say that the jack is the opposite of the clock. And next slide, please. Let's see. Okay, demo. Let's see if I can try this. Okay, so I think I have it on the other camera. Do I? No, that's the other. Let me, I'll put it on this camera. Zoom back. I get my glasses on, pardon me. My sight is failing. Let's see, there's the project. Okay, so we'll zoom in. Like these four jacks. Let's see if I can get the lights on. Okay. And they're just really something. So if I were to operate that. Okay, wait a minute. Let's see. Okay, here I'm cranking it up. You can hear the clicking of the pawl. And the beauty in this jack is that there's no spring in it. It's all the pawl. It slips on a tooth, and then its gravity pulls it down. And then if all I have to do is then flip it over, it's got just the right shape, and then it goes in the other direction. Okay, so it's a swing to not only to a rising weight, but also to a falling weight. It needs some weight on it in order for it to come down. Okay, so I would argue that that's the opposite of a clock. And that was from a Model T, yes. So let's go to the next topic. How am I doing on time? Okay, so the next one I want to look at is the piston as the next engineering idea. Next slide. And we're going to look at a pitcher pump. Next slide, please. And the piston is the plug that moves inside of a hollow cylinder. And it's attached to the crank. Next slide. So we're going to start with another formula. This simple one. We'll start with first, what is the volume of the cylinder? Well, it's the area of the piston times the length of the stroke. So now, by the way, this is a formula that's symbolic. It's visual. It tells me how big my object is. So remember I talked about relationships? So that's an important relationship. If I have a large volume, that means I have a large object. If I have a small volume, a small object. I could even go further and talk about aspect ratio. I could have something long and thin or short and fat. Right? But I'm not going to, for now, I'm just going to talk about the volume. Next slide. Now here's how these pumps work. In the base here, there is a foot valve, which is a piece of leather that's weighted. And everywhere that's blue here there's water. And then the piston has another flat valve. There's a bucket associated with this. And that valve can open up in one direction. Okay, so it can open backwards to let water through. And then the one at the bottom can also open in that direction and let water up, but not in the other direction. It's a one-way valve. And it said, let me just read what it says here. The bucket pump is submerged in water at its lowest level. As the piston or bucket descends, the flap valve in it opens and water rushes through it. So in other words, this bucket slides through it. As it rises, the valve shuts. So as it's going in the other direction, the valve's closed. And then it pulls the water above it up. And then it also creates a suction below and draws more water up to fill the chamber. It's like sucking water up the chamber. As it rises, it shuts, suction opens the foot valve, and the pipe fills with more water. Next slide. And here we see an image of that. So here we see the bucket with there's a valve at the top and a valve at the bottom. Next slide. And as it's moving up, the valve on the piston is closed, but the one at the bottom, because there's suction pulling water up, it opens. Next slide. And then when it gets all the way to the top, they're both closed. It rises. It's weight. It's driven down with weight. Next slide. And here we have another formula. Okay, so the stroke length that's there is L. The area is A. So again, we have that volume. So one stroke will take that volume's worth of water and lift it up, and then it will spill over the end of the pump. And then if you repeat that at a rate n, so n strokes per minute, for example, then you get a flow rate, Q, which is volumetric flow rate, cubic feet per minute, for example. And it shows you how the pump converts motion to flow. Next slide. And then going down, it will go down and opens up again and then repeats the cycle. Next slide. So this is the first animation I ever made. I went down to our machine shop and learned how to use our 3D software. And it's 16 images showing how it's going up and down. You have to look very closely to see the foot valve opening up. And then you can, if you look closely on up in the cage here, you can see that plug is moving up and down as the water is going. Hold on a second, I want to get the sound on this one. It's on? Oh, it wasn't. Okay, great. Okay, so let's go to the next. So the next one, you can go to the next image. Okay, and sometimes I bring this to the lecture hall, but it's a lot of work. So this is one. So note the color scheme on these. This is Princeton, of course. So it's here we see. Notice what I was doing was pouring water in there, timing the pump. You have to have water. And this is a great. You can hear the water rushing. This is great if you have little kids, right? Because it recirculates back into the bucket. It's absolutely nothing but keeps you entertained. So it's a great thing to use. I thought it would also be great for you use it for dispensing beer. The problem is the beer would get kind of flat. But you could use it on a table, right? You could use it for your drinks or something. So soda, not soda, nothing carbonated. But you could pump it and use it for filling your glass with your glass. Okay, next slide. Okay, so now we come to the steam engine. And here we see a patent drawing. It was a patent that was laid before Parliament in 1775 by James Watt. Next slide, please. And what we see here, again, is this idea of reversibility. These beam-type engines, they were initially used for pumping water out of mines. So remember pumps, water pumps? So on the left-hand side is you had a piston and a pump. Now some of these pumps were suction pumps and some of them were compression pumps, but they still had a piston and a set of valves. So that was the left-hand side. And then the right-hand side was a steam engine. And the steam engine is a piston-type motor. So the pump and the motor, we're going to see, are opposites of one another. Next slide. I'm going to get this light off. And to understand how the steam engine works, these early steam engines were worked on the basis of a vacuum. Later steam engines worked on the concept of high-pressure steam. So the idea is that the beam, the piston on the pump side was always heavier than the piston on the motor side. So if you left it alone, it would always want to rock in this position. And then what you would do is you would introduce steam into the motor. So you'd introduce steam into this area. So you see it says hot steam comes in, and the piston would be up at the top. And then you'd close off the valve, the steam valve, and then you'd spray in some cold water. And the water would condense the steam. And when you go from steam to condensed steam, water, you create a vacuum, pretty good vacuum. And so this region would be evacuated, and there would be atmospheric pressure on the top of the piston and vacuum below it. And so therefore, the pressure difference would push the piston down. So the action here is a downstroke. So it's vacuum to work. And it's also a transformation of heat to work, because you have to make the steam, you have to heat the water to create steam. Next slide. And then James Watt came up with a formula to describe the equivalent number of horsepower to these engines. And notice our familiar LAN now. That was our flow rate, but now we add to it pressure. So pressure times flow rate is power. Another way to group that is P times A is force, and L times N is velocity. You may know power as force times velocity. So, and then the 33,000 was James Watt's estimate of the equivalent power of a horse. And this is in units of foot-pounds per minute. And he used this as a way to make money on his steam engine. And we see that P is the pressure, L again is the length of the stroke, A is the area, and N is the number of strokes per minute. Next slide. And in a pressure engine, same formula applies. So the later engines were pressure engines. But here what you do is you apply high pressure steam, and if you apply it to the bottom side, so the pressure is high here and low on the other side, it pushes the piston up. And then if you reverse and apply the high pressure steam to the top and push it down, you'll get movement again. So that's based on a pressure engine. Those were the engines after about 1800 were pressure engines. The early engines were, for the most part, vacuum engines. Next slide. And here's now Watt's engines of the later period, in about 1780 and later, were mixed. They had some pressure and some atmosphere, so it used a combination of the two. And we look at his, here's his rotive engine, his rotary engine. So the early one was just a straight beam engine. And what we see here are the different parts. Here's the piston and the cylinder. That's the motor, from what we saw before. The fuel is coal. We put coal, we use it to boil the water into steam, and the steam gets emitted into the motor. And then, again, there's a governor, a speed governor. So those same elements we saw before, motor, fuel, and governor, are replicated in the steam engine. Next slide. And here's an animation of his double-acting rotary steam engine. The date's about 1782 is when he came in with this. And unlike the early beam engines, which only pulled down, this pulls down and pushes up. And he had this very clever little linkage over here that would allow you to actually push on the beam. And then the flywheel keeps the thing spinning in places where the mechanical advantage is not good. These engines, if you don't start them just right, they get stuck. Next slide, please. And here is one of these little beam engines. Note that I'm driving it with an air pump, so it's a piston pump. And so motion to pressure, and then the pressure goes to the steam engine, pressure to motion. So this is this idea of reversibility. And why I wanted to sound on it, I wanted you to hear the chuffing that's going, because the chuffing has to do with the sound of the air or steam coming in and escaping from the cylinder. Next slide. So, by the way, that engine was an engine that was made by a Princeton grad, a lawyer, who, just for fun, read Popular Mechanics back in the early 30s and made steam engines. We were given about 50 engines. That's one of my favorite ones. I especially like the beam engine. And we use it in our, I use it in lecture demonstration. We also use it in a laboratory in my course. Formulas again. So animals versus machines. How many horses are replaced by the steam engine? Once again, our formula is itself symbolic. So it's the formula is the symbol of that equivalency. Next slide, please. And here's an artist's view of it. Here we see a winding engine, and we see there's coal being brought up out of the coal mines that's being helped along by the winding engine that's helping to pull these cars up. And we see that the steam engine eventually will replace the horses. So it's telling us about the transformation from animal power to machine power. Next slide. Now we also, in 1877, this is at the time of the American Bicentennial, a German salesman and engineer, Nicholas Otto, developed a new type of engine. This is the engine that he displayed in Philadelphia at the Centennial Exhibition. It was patented in 77, but displayed in Philadelphia in 1876. Next slide, please. And again, it works by a piston and a flywheel, some of the same parts that we saw before. But whereas the steam engines were external combustion engines, you burn the fuel outside the chamber. This is internal combustion. You burn the fuel inside. Next slide. And here we see Henry Ford. The date's about 1893, and he is quite taken by these internal combustion engines. He did not see this engine in Philadelphia. He was too young, but his father attended the Philadelphia exhibition, and he was Ford himself was quite interested in engines. And what we see here is a single-cylinder Otto engine. This thing is turned on its side. Here's the flywheel. His wife Clara is helping him in her kitchen, no less, and he's playing with this thing, and he gets this engine going, and he uses his success in making engines ultimately to turn automobiles. Next slide. And this is the Model T engine. It's a 4-cylinder engine that is based on this Otto cycle. Next slide. And the important thing here is we see its pistons again, and it's a crank. And the fuel in this case is fuel and air that's introduced into the chamber. There's an explosion. That explosion is caused by an electric spark. That increases the pressure. It pushes the piston down, and it causes it to run. This is Margaret Soroka. She graduated from Princeton 2 years ago. And here she is working on one of the engines that we got with the Model T. And here is the engine upside down, and she's making some measurements on the engine. Next slide, please. We also, we took the engine apart. An important part here is we see the pistons, and we see the cylinders, the 4 cylinders associated with it, with valves that are needed for bringing in the fuel and air into the chamber and getting rid of the waste gases. Next slide, please. It's the demo. Okay, so let's go back to our demo. So now let's take a look at this toy engine. I think that's the other camera. Okay, so I'm going to crank, there's an engine here that I had a student make a number of years ago to help explain how this works. And the various parts here, there are valves here. So there's an orange piece that connects, this is the exhaust valve, and the white ones are the intake valves. So this is one cylinder, this is another cylinder, there are 4 altogether. And there's a little light bulb up here, which is a little, that simulates the spark. And what I'm going to do is we'll start with it sparking. So I'm going to increase this to the point where it sparks. Let's see if we can get the light going. Can you see the light firing right here? Okay, so when the light fires, the pressure is large. It pushes the pressure, it's a high pressure, pushes the piston down. As the piston comes down, the valves will stay closed. Let's just take a look at that. It goes to the bottom. Then and the second one fires and it pushes down. But then the first one comes up. It's being driven now by the second cylinder. And as it's coming up, this valve will open up. That's the exhaust valve. See it's lifting up there. Okay? And then it gets to the top and then it lets the waste gases out. And then on its way down, whoops.
Is that too dark?
Well, maybe it's, we can see. Here you can see the intake valve opening up. Okay, that's letting the fuel and air in. Now it's going through the compression cycle. It goes to the top, and then it fires. Okay, so I can do that again a few times so you can sort of see. You can see the valves going. You can see the valves in each one of the different cylinders moving up and down. And then they're firing, and then this particular one has a firing order. This is a 2-scale model. This is the size of the Model T engine. It's a 4-inch diameter cylinder and a 4-inch stroke. And it has the valve, the firing order in the exact same way that it's done. And it has cams and push rods and everything in the same positions that they are in the Model T engine. And it was intended to help you understand how this thing operates. All made out of Kinex with the exception of the gear over here. There wasn't an equivalent gear, so we had to manufacture that ourselves. Okay, let's go to the next. Next time. Yeah, okay, good. We're in good time. Okay, so this is now an image of the Ford Motor Company. The Ford Model T was introduced in 1908. We're coming up on the 100th anniversary of the Model T. So pay attention, October 1st, 2008, there'll be a celebration. Actually, there's a conference. It's at Greenfield Village, Ford's history museum. They were running in honor of that event. The Ford Motor Company starts in 1903. And here we see Henry Ford looking at his 1896 vehicle and his son Edsel Ford looking at the 10 millionth Model T. So it's a 1924 Model T. There's also a little bit of local history on this. It says on the side, it says New York to San Francisco on the Lincoln Highway. Right? Well, we live on the Lincoln Highway. That's Route 27. Okay, so this vehicle went right by Princeton, for sure. And the Model T that we have is from 1921, and it was the 5 millionth Model T. So there were a total of 15 million Model Ts made. It was the second largest production run of any vehicle in history. The first being the Volkswagen Bug. In the early period, if we think about the Ford Motor Company was dominant. Let's go back to the economics. It dominated the automotive industry. More than half of the vehicles on the road in the world were Model Ts. And so it was absolutely dominant until the end of the period, 27, and then General Motors comes in. And then General Motors takes over. Next slide. So here was a stamp that was put together in honor. It's rather odd. It was done on Henry Ford's birthday, July 30th, but it was done in 1968. He was 100. He would have been 105, not 100. So I think somebody just slipped and they just figured they wanted to do the 100th anniversary of his birth and they missed it by 5 years. So here we see Henry Ford with his Model T. Next slide, please. And here we see Tofik and myself driving our Model T. Next slide. And now this is, again, the artist brings us back and sort of says, well, what's this all good for? This is Norman Rockwell. It was a commissioned work at the 50th anniversary of the Ford Motor Company. So it was in 1953. And the title of this is "The Street Would Never Be the Same." And what we see is Henry Ford on Bagley Ave driving his original vehicle, the 1896 vehicle. And what it's doing is it's making a lot of smoke and noise. Somebody's holding their hands over their ears and scaring the horses. And it's causing quite a commotion. And the street never really would be the same. Because if we think of the transformation, it's the end of the horses. Right? So it was a transformation from horses to automobiles. And it also reminds us that the automobile is a noisy vehicle, and it's smelly, and it's, has lots of things that are not particularly attractive. Next slide. Okay, now let's come to the our last group here. We'll look at the diaphragm and the spring. Next slide, please. And we're going to turn our attention to phonographs. And the phonographs we'll look at, this is an Edison phonograph. This particular one in the picture is a gem. It was the iPod of its day. It was the portable. The ones I have with me are home versions. There's a standard and a home that I brought with me. And then there, if you look under the hood here, you look at this is what you'd see on the underplate over here. And if you took this apart, you'd see this thing with the springs. Next slide, please. And then the pieces that I want to pay attention to here are the diaphragm. So diaphragm, it's like the diaphragm in your ear, like your eardrum. The diaphragm that you have in your chest cavity. It's a thin membrane. It's an important idea for transformation. And then spring is another important idea for the phonograph. Next slide, please. And thinking now of our idea of fuel, motors, and governors, once again, we see this in the phonograph. These are crank phonographs, so you turn the crank, and what it does is it tightens up this coil spring. So you're providing fuel. And then when the tank is full, the coil, the spring is all wound up. So it's very tightly wrapped around the shaft. And then as it gives up its energy, it unravels. It then causes this whole body of the motor to unravel. And in the process of doing it through gears, goes to a belt, which then spins the main wax cylinder. And then there is a governor in there, like the governor in a engine. It's actually a flyball governor that regulates its speed. So it has all of those same elements we saw before. Next slide. And this was in Edison's lab notebook. Let me just read it here. It says, just tried an experiment with a diaphragm having an embossing point, a needle at the end, held against paraffin paper, so paper with some wax on it, moving rapidly. And then the speaking vibrations are indented nicely into the wax. And there's no doubt that I shall be able to reproduce automatically at any future time the human voice perfectly. So this was his comment in his lab notebook. The date's 1877. He called it his favorite invention. It surprised him because it worked the first time that they built it. It was really quite something. Next slide. And here we see, shortly after doing this, what one did in those days is you took your invention and you showed it to the president. So I believe the president then was President Hayes. And it was in 1877. And the diaphragm is right up here. He has a hand crank here. This one doesn't use a spring. He's got a cylinder with his paraffin paper. And in the later ones, the ones like this Edison, the ones that I have with me, the diaphragm is just a thin membrane of corrugated metal. And then the stylus is either a little sapphire bead that will track it moving, or in the recorder, by the way, these are both recording and playback units. In the recorder part, it will actually cut into the wax. Next slide. And it says demo the Edison player and an Edison recorder. So I have two with me. First, let me demonstrate the player. So I have a unit here. These are crank units. Let's see. So I think maybe I can get the camera up on this. Everybody can see it. Let's try this other camera, and then I will this over to these photographs. Okay, stand in front of this for a second and turn the crank. You want to be careful not to over crank the springs on these. They can come unhooked, or you can snap them. But I'll get this going. I think this is a rag. That's a rag. So now what I want to do is we're going to try a little demonstration. I don't know, is anybody here an a cappella singer? Volunteers? For the college students, there's always somebody from one of the singing groups. Does somebody have a booming voice that I can get as a volunteer? You want a booming voice? You'll do it? Okay. So what I'm going to do is I have a soft wax cylinder. The second machine over here, I have a cutting head. And the cutting head is the one that reproduces is just a little bead of sapphire. So it's round at the end. And this one's cut off sharp, and it has a sharp point. And it's, again, attached to a diaphragm. And what I'll ask Mark to do here is we will, you can actually, the famous first line is Mary Had a Little Lamb. So if you know that one, what you need to do, Mark, is I'll get it going. And you need to speak into the bell and speak loudly. Okay, not until I get started. So what I'm going to do is I'm going to drop it. Okay, go for it.
Mary had
Louder.
a little lamb. Her fleece was white as snow.
Louder.
Mary had another lamb. Her fleece was even whiter.
Try it again. Say.
Mary had two lambs. Their fleece was very white.
Okay, and you can say hello, hello, hello.
Hello.
Okay, and let's see how that works. Okay, so let's see if this is successful here. I think it will be. So you can't see this here, but there are now shavings on this soft wax cylinder, which I'll blow off. And then I will put them on this other phonograph, and we will play them back. We'll see how well Mark did. Okay. It used to work better. These wax cylinders over 100 years have dried out. So the way to do this right is you're supposed to sort of warm them up a little bit, or there are reproduction. These are original clear wax cylinders that I was able to get. So it's, the fact that it works at all is almost a miracle. Okay. And I brought several with me today, and the first one I tried didn't work terribly well. This one worked better. Okay, next slide. We're almost done. So again, stamps help us. Note this is a stamp. It was in 1977. Remember, it was 1877. It was the 100th year of sound recording, not of the phonograph, but of sound recording. And note the image that's there, and then look at the picture of Edison. I forgot to mention that picture of Edison. That was taken by Matthew Brady's establishment. So this was a Matthew Brady photograph, not Matthew Brady himself, but by Matthew Brady's assistant, and you see that the unit is the same one that Edison brought with him to show the president. Next slide. And now here's another painting, his master's voice. So this is Nipper. You probably have heard of Nipper, right? But you've probably thought about it in the context of the phonograph. And if you think about Nipper, it's his master's voice. right? It doesn't make a whole lot of sense. You know, why would his master's voice be on a record if it wasn't also a recorder? So if you look very closely on this, this is the first one of these. Nipper was owned by somebody who had an Edison machine, not a Victor machine. So what you see up there is an Edison phonograph, okay, with a wax cylinder on that. And so he's listening to his master's voice because he just did the same thing that I did and was confused by it. And then this fellow died, I've forgotten his name, and then his brother got Nipper and also was also a painter. And so his brother painted next slide. Painted this next image, but now it's a Victor machine, a platter machine. And here we see Nipper again, the same Nipper listening to his master's voice. Next slide. And then that became the trademark for the Victor Phonograph Company from Camden, New Jersey. And it says his master's voice here. We see that Nipper's listening.
We know what Nipper is standing on.
What is Nipper standing on?
He's standing on his master's coffin.
Oh, is that right?
Yes.
Oh, I think you might be right. I think I do remember that.
That was the dog he's listening to.
The master's voice on. That's great. That's great. Didn't know that. Next slide. And then, of course, this got picked up by the RCA. The Victor Company in '29 was sold to RCA. RCA was very interested in phonographs and radios. They picked it up as a symbol, and then it became the symbol of the RCA Corporation. We have a sort of a local corporation. Thinking of things that are local, I also brought in another phonograph and a record here. I thought that this one would be very appropriate for Princeton. Let's see, get this one working. So this is what they call as the dog horn phonograph. So it has the Nipper on the side with a little label. It's in not great shape. You can sort of have to use your imagination to see that it's got Nipper on it. But if you look at the label on the side of this, it has one of these labels, and this is. Let's see, I'm doing this backwards. I always do it from the front. Just make sure I get it on the right side. Yeah. So who's singing? Paul Robeson, okay. And if you know the story of Paul Robeson in Princeton, this is an appropriate song for us. Paul Robeson had a wonderful voice and a really deep bass, and it really matched these phonographs. So okay, so in any case, these are 78 RPM. So these are lateral cut, and I wanted to finish up with this. So in the Edison ones, they're vertical cuts, so the diaphragm moves up and down, whereas on these Victor machines, there's a diaphragm again, and there's a needle, a steel needle that moves in a groove, and it's moving side to side. But again, it's a transformation of sound from the vibrations from the motion to the diaphragm, which then moves the air that produces the sound. Next slide. We're almost done. So just to sum up what we've got here, think of engineering works, 17th, 18th, 19th, and 20th century. The clock with Huygens, what, who, when, where. Huygens, middle of the 17th century, it's Holland, pendulum. Information, steam engine, power. Okay, so this is in the middle of the 18th century, 1769 was the original patent. It's in Scotland, he's Scottish, and then he moves to Birmingham. The phonograph, Edison. Edison, of course, is in New Jersey, invents this in Menlo Park, using the diaphragm. This, again, is information. So this information, power, and then, of course, the automobile with Ford, 20th century, that's transportation. And we see that that's 1908 was the Model T in Michigan, in Detroit. Next slide. So now thinking about the 21st century that we're in, and you say, it's, of course, we give to students, you say, what's going to happen? Well, we don't know what's going to happen. But what I'm certain is that the three categories we talked about, next slide, three categories, power, information, and transportation, will be represented, that's for sure. Next slide. And it will involve structures, machines, networks, and processes. So it's going to clearly involve engineering works in that period. It's also going to be affect our economics. It's going to affect our politics. It will affect our culture. Next slide. And remember reversing, this reversibility. This is one of my favorite images from Lewis Carroll. And it's the White Queen. And Alice here is a pawn to the White Queen. The White Queen is a chess piece. This is from Through the Looking Glass. And the White Queen has a memory that works backwards and forwards, because she, as a chess piece, can move backwards and forwards and diagonally. Whereas Alice is a pawn, she can only move in one direction. And the Queen comments, it's a poor sort of memory that works only backwards. Now this is symbolic for us, because why should one learn the history of technology? It should be that not just that you remember the past, but you should be able to apply it to the future. And it's a message that I like to deliver to our engineering students. And then another message to our engineering students is that we talk about their skills. And let's go to the next one. Let's see.
I'm worried about little Dilbert. He's not like other kids.
What do you mean?
Yesterday, I left him alone for a minute, and he disassembled the TV, our clock, and the stereo.
That's perfectly normal. Kids take things apart.
Oh, the part that worries me is he used the components to build a ham radio set.
Oh dear.
Is that bad?
Normally I'd want to run an EEG on him, but the machine isn't working. It's worse than I feared.
What is it?
I'm afraid your son has the knack.
The knack?
The knack. It's a rare condition characterized by an extreme intuition about all things mechanical and electrical, and utter social ineptitude. No. You'll be an engineer.
So what do we say to our students who want to change the world, and they have the knack? Next slide, please. We tell them, become an engineer. I'm sorry I went on a little long, but it's, I certainly would be happy to entertain any questions. That comment about the coffin, that's very interesting. I appreciate that a lot. I think I remember hearing something like that, but that's...
When you see the whole painting.
The whole painting, you can see
It's coffin at large. The small section you showed is the common example, which only shows the photograph and the pillow, and you can't see the whole coffin.
I don't, everybody heard that. You see the whole painting. I'm going to have to get a copy of the whole thing. By the way, the internet is wonderful for getting these images. It's just, so all of them are pirated, but there's a principle known as fair use. So for lectures, I'm able to do it. I can't turn around and sell these images, but I'm able to sort of capture them on the internet. Yes.
Can the wax this be redone, renewed? Or?
Yeah. So okay. So there is a. So the question is, can the wax be reused?
And how?
And the answer is yes. So there is an attachment on these units that known as a shaver. And you just take a piece of cut glass, and it moves along with the spindle, and it actually will shave it. Another way to do it, which is the cheap way to do it, is just take a rag with some gasoline, which dissolves the wax, and then just wipe it on and let it dry, and then you can reuse it. And the way I did it is I use very fine steel wool, and actually do it that way. For a while I was putting them in the lathe. The problem with the lathe is then you wind up taking off too much wax because they get to be a little uneven. So if you want to save them, there's enough, they're thick enough, you can use them hundreds of times.
Can you reconstitute? Can you add wax back?
Can you add wax back? Well, there's a fellow in the Midwest that sells modern wax, so they have a process for doing it. It's not, it is a hard wax, and it's a wax compound. And I don't know the details of what's in there. But what I do know is that if you encounter the brown wax cylinders ever, look at them, before there were mass production recordings, everything was done individually recorded. And the brown wax cylinders are more valuable. Some of them have unique recordings on them, and speeches and whatnot. So if you ever come across one of them, first see if you can play it. If you can't play it, then you can wipe it. Yes, there was a question over here.
On the steam engines,
Yeah.
a pressure steam engine seems a lot more obvious than a vacuum steam engine. How come the vacuum steam engine came first?
Okay, so I don't know if everybody heard the question. The question was, pressure seems better than vacuum. And it is. It's a more efficient engine. The question was, how come the vacuum engine came first? It had to do with the quality of the cylinders and the quality of the seals, and that was the main piece. And also the safety of the cylinders. A pressure engine, these were large engines, and so the forces on them could be quite large. And James Watt and his partner Matthew Bolton made mostly vacuum engines, and they really held back the progress of high-pressure steam engine. But high-pressure steam has its problems. In addition to being potentially dangerous as in rupturing not only the boilers but also the cylinders, but steam itself is very corrosive. So it gets into the porous areas, and you find you get a lot of wear to the cylinder. But the original reason, if you read the early literature on this on Watt, there's a great biography of Watt by Dickinson. It's sort of the best biography. Was written in the 30s. It talks about seals. They were using leather seals. They were using horse muck to actually seal them up. In addition, they were very leaky. They just didn't work very well. There's one other issue with the vacuum engine. The power stroke was down. The beam is basically part of a pulley. It strikes an arc. So think about trying to couple a shaft that's moving straight up and down with the end of a beam that's moving on a curved path. Okay, they don't match, right? And so on a downstroke, if you hook the chain on it, it works just fine. Okay, so you can pull down, but you can't push up. That's why Watt was so pleased when he came up with that linkage that would allow you to pull down and push up. So it provided a coupling between this arc motion with the linear motion of the cylinder. Okay, so that was one of his, another one of his great inventions. Yes.
The unit of measurement in electricity, the watt, was that named after?
Yes. So the question is, was the unit of electricity named after James Watt? And yes, it was. There was an international naming convention. There are a number of units that were named after great people that we admire. A lot of the electrical units. I mean, Watt was power. He was the one who came up with this power formula. That's the formula for so-called indicated horsepower. But the amp was named for ampere. The farad was named for Faraday. Our own Princeton's Joseph Henry. The unit of inductance was named Joseph Henry. The coulomb, unit of charge, and so on. So a lot of these units, the ohm named for ohm. Now, on the one hand, it's great to honor people like that. But I would say I really like the unit of foot-pounds per minute, right, for power, right? Because you know what a foot is, you know what a pound is, you know what a minute is. You know, what's a watt? What's a horsepower, right? You know what at least horsepower is a good unit. You know what horsepower is. But on some of these other ones, it's kind of hard to know. Oh, a great one for those that know telephones, the bell. The decibel, right? Well, that's named for Alexander Graham Bell. And then the unit that they had was too large, and so instead of using a whole bell, they needed a tenth of a bell. So that's the ohm, yeah, the name was for Gustav, I think it was Gustav Ohm, yeah. Yes, a question here.
The idea of reversibility is so interesting, also microscope and telescope.
Right.
Do you have any ideas about the future of reversibility?
Reversibility. Well, I'm certainly, so the reversibility from physical principle comes about, my training as a physicist. So it really drummed into you about the idea of time reversibility, or charge conjugation, or whatever. So you're always looking at things in backwards. So I'm very much taken by this idea of reversible, and it's only true of conservative systems. So conservative means energy is conserved. You don't have loss, and a lot of these systems are lossy. So I find it very attractive. And every time I think about engineering works, I like to think of this idea of reversing. And there are many others that we've thought of. The water wheel and the paddle wheel, right? So the water wheel that's used on a mill and a paddle wheel on a boat. So propulsion. So, but in terms of the future, what I can say is that that reversibility is not going to go away. I mean, I think there will be future objects. I think what it does is it helps you think in a different way. When I was thinking about that clock and then thinking about the jack, what's the opposite of it? It gets you thinking about how you might use an object differently. So when you think about a clock with a falling weight, right? You think about a clock as measuring time, but you could also use it as a regulator for regulating a falling weight, right? So it's just another way to think about it, and I think it's actually helpful. And one other thought that relates to it has to do with Newton's law, F equals ma. So the physicists talk about F equals ma as a description of nature. So a mass acted on by a force has an acceleration. But the engineers tend to look at F equals ma in a different way. They look at it as a conversion. Now this is actually a little deep, but I think it's a good way to think of things. So what a mass does, if I have a mass and I apply a force to it, it converts the mass. The mass converts the force to an acceleration. And a spring converts a displacement to a force. And if you want to know how to make an accelerometer, that's a mass attached to a spring, in a box. So if you accelerate the unit, so what happens is the mass converts the acceleration to a force. The force converts the force to a displacement, and then you measure the displacement. That's how you measure acceleration. So you can use this idea of conversion. The engineer thinking of conversion, where the physicist talking about a description of what happened. It's a different way to think of things. Yes?
The reversibility is fascinating, but I think you're shortchanging irreversibility.
Okay.
Thermodynamics. In your demonstrations here, you have valves, you have ratchets, you have things that keep the motion going in one direction and not allowing it to turn around and go the other direction.
That's correct.
And it seems to me that that's a really conceptually a huge idea in any kind of system where you start with something that could be sort of entropy or vibration of some sort, and you turn it into a one-directional motion.
Okay, so what you say, so it's a comment that irreversibility is also an idea, and it would be a complementary idea. So I was talking about conservative systems, a way of thinking of it backwards, and you're talking about systems that are more real, and in these cases are real, and it's clearly it's another good point. Probably a whole other lecture that goes along with it, or certainly another aspect to it. Certainly thermodynamic efficiency, reversibility would play in a big way. Yes.
So in our world where sound recording is so ubiquitous and MP3, why are we so fascinated by that demonstration?
Why are we
so fascinated?
Why are we so fascinated?
In a world where electronics.
Well, when Edison first introduced this, people thought he was having ventriloquist with him. They thought it was a fraud, and it was just something that was so different, so alien to what people thought was possible. And then primitive peoples felt that you had actually captured something from the person. It's like photography also played that role. I think that just the idea, it's very personal, I guess would be the way I would describe it. And you're capturing a piece of a person and replaying it back. I think that's probably the fascination. And then you can play it back at will. So there's sort of a power that goes along with it. I'm sorry? It is history, yes.
Plus the other simplicity of it too.
Yeah, it's really, well, the idea that a diaphragm, well, and I didn't talk about the early history of this. The person who really took advantage of the use of the diaphragm was Bell, Alexander Graham Bell, who was a teacher of the deaf, and he studied the human hearing, and he understood the idea of eardrums, and basically the mechanical advantage you get from having a fine drum associated with it. But it is the thing that draws me to a lot of these antiques, especially the earliest ones, is the simplicity in the devices. So that where an automobile today, if you took apart your Toyota Prius, you're going to need a lot of time. But let me tell you that you can take apart a Model T engine, and it's beautifully simple, and it works really well. So there's a real attraction for me to look at these very early options. Maybe I think we probably have enough questions. Okay, thank you.